Hello everyone, welcome back to my channel. This is lecture 14 of the lecture series Signals and Systems. In this video, we will be starting with discrete time signals. So firstly, we will review some of the basic concepts which we discussed in lecture 1, such as the size of a signal, transformation of independent variable, classification of signal, and finally we will see some useful discrete time signals. So let's get started. So as we all know, in discrete time signals, the independent variable is discrete in nature. Independent variable is discrete in nature, and we represent it by x of n. So n is integer, right? So how will the signal look like on graph? So we have the independent variable n, we have the signal x of n. So we'll have 0, 1, 2, 3 and minus 1, minus 2, minus 3 and so on. So our signals will take on values like this, right? Can also be 0. So you should note here that only the x-axis, the independent variable, is discretized. But on the y-axis, the signal itself can take any values. Okay? So this can be any value, any amplitude or value, let's say. It belongs to real numbers. Okay? The value taken by the signal is still continuous. Okay. So where do we encounter such signals, right? That is our next question. Where do we encounter such signals? So mostly, as a general example, we encounter it in demographic data. When we are collecting the data regarding groups, right? Let's say like male and female. So this will be your independent variable having two, male and female, or let's say number of years, right? For each year, let's say 1999, the GDP is this much. 2000, the GDP is this much. So when you're calculating it with respect to the years and so on, okay, that way, right? But for our context, in our context, it is usually obtained by sampling the continuous time signal. So you have a continuous time signal. Because why are you sampling it? Because you have to finally convert in this analog signal into digital format so that you can do all your processing in digital, so that it is easier and faster. So that is the main idea, and the first step towards converting it to a digital is sampling. So then let's say you're sampling at these places. So then you will have this one, right? So we'll see some interesting properties about this sampling later, but for now we'll study about the discrete time signals. So in our context, discrete time signals is obtained by sampling the continuous time signal. Okay, so now we'll see about the size of signal. This we saw earlier as well, size of a signal. So what is the size of a signal? It is the measure of strength and largeness of a signal. And what parameters did we want to take into consideration? Both the amplitude and the duration. So your duration is given in terms of n, correct? So higher the extent of the signal in the time axis, more should be the size of a signal, right? Let's say if you have this signal, this is only relevant here. Let's say all other places it is 0. And you have other signal, it is having a constant amplitude and extending to infinity. Of course, you can try it out and see. We need to find which one we say is a bigger signal, or we need to have some measure of the size of a signal. So for that, we have what is called as the energy of the signal. So it is given by Ex, and since it is discrete in nature, we are going to square each of these terms. So x of n whole square, and we are going to sum it up. So summation n equal to minus infinity to infinity. Okay, so this will give you the energy of a signal. Again, why are we squaring? We want to eliminate the negative terms also. If it is a big signal with negative, it is also considered as a big signal, right? Not just in the positive direction. So to eliminate that ambiguity, we are just squaring the signal. So this is for real. For complex signals, it will just be the modulus mod of x of n whole square. Okay. So again, there is some limitation in this, because if it is extending from minus infinity to infinity, this is going to tend to infinity, right? So the energy will tend to infinity. So then we define something called as the power of a signal. So how did we define power signal in analog terms? For continuous time, we had Px as limit t tends to infinity 1 over t integral minus t by 2 to t by 2 x of t mod square dt, right? For both real and complex. So here, if we try to get a similar thing, we'll get some n by 2 in the summation. We don't want that. So we'll just modify this a bit. So limit t tends to infinity. We'll take 2t time period, okay? A period of 2t. Minus t to t mod x of t whole square dt. Okay. Now we'll try to modify it for this case. So px is nothing but we have x of n mod square, and we need to sum it from n equal to minus n to n, right? And we need to divide it by the total number of terms here. So what will be the total number of terms from minus n to n? So we have minus n plus 1, and we have 0, and then 1, and then n minus 1, n. So how many terms are here? For example, if I have to take n equal to 1, we have minus 1, 0, 1, 3 terms. N equal to 2, minus 2, minus 1, 0, 1, 2, 5 terms. So for n equal to n, we'll have 2n plus 1 terms, right? It's not 2n, it is 2n plus 1, because we are also including the 0. So 2n plus 1, okay? And we want to take limit n tends to infinity. So this will be the power of a signal, and it is nothing but the time average of energy. right? So let us try to see some examples. So let us take a simple. So let's say this is 4, 4, 4, 0, 1, 2, and everywhere else it is just 0. Okay. So this is my x1 of n and n. So what will be the energy of this? So Ex1 is nothing but summation n equal to minus infinity to infinity x1 of n whole square, which is nothing but 4 square plus 4 square plus 4 square. Again it is 16 into 3, right? Which is nothing but 48. And what is the unit here? Let's say this is in units of volt. So this will be whole square. Because when we discretize, right, we remove the second in the time or any independent variable. Because it's just an integer, right? So we treat it as just an integer without any units. Okay. If you give units, then you have to write it as whole square into that unit. Okay. It's simple. So as a second example, we'll take something for the power calculation. Here what will be the power? So it will be 0 because your summation term is going to be finite after n equal to 2 for beyond n equal to 2, right? And this term is going to tend to infinity, which means your entire expression will tend to 0. So example, let's take this example only with this continuous thing. So 0, 1, 2, 3, 4, 5 and so on. And same on the left side. Minus 1, minus 2, minus 3 and so on. In x2 of n. And then let's say each of them is 1. So what is the energy of this signal? Summation n equal to minus infinity to infinity x2 of n whole square, right? Mod square or just simply square. So this is nothing but summation n equal to minus infinity to infinity 1 square. So this is going to be infinity. So we'll just calculate the power. So my power will be limit n tends to infinity 1 by 2n plus 1 summation n equal to minus n to n 1 square, right? X of n whole square. And this is going to be equal to 1 square. And this summation is going to be 2n plus 1. So the 2n plus 1, 2n plus 1 cancels. So it will just be limit n tends to infinity 1. So which is nothing but 1 itself. So the power of this signal is going to be 1. And what will be the units? Again it is in whole square. So here you can see both energy and power is having the same units. But again it is only for our convenience to quantify the size of the signal. So it is going to be okay. So next we'll look at the transformation of independent variable. So we have 3 transformations. The first one is time shifting. So the second one is time scaling. And the third is time reversal. So time reversal can also be part of time scaling if the coefficient is going to be negative. So anyway, we'll consider it as a different and see how it goes. Okay. So first we'll start with time shifting. So let us consider a signal x of n. This is n. And let's say it is given by this kind of pulse-like structure. So 0, 1, 2, 3, 4, minus 1, minus 2, minus 3. So now we'll just try to shift it by some t units. Okay. So n. Let's call it a new signal phi of n. I'll shift it to this to the right by t units. So what will I get? My amplitude will remain same. I'll take 1, 1, 1, 1, 1, 1. So 0 will go to t. This will be t plus 1, t plus 2, right? And here you will have 0, 1, 2, and so on. This side minus 1, minus 2, and so on. So my amplitude remains same, and the signal is shifted in time by t units. Again, this t should be an integer because we are only considering integer. So we can just write this t as some n naught, okay? Since then it is easier to see it as an integer. So by n naught units. So what can we see from here? Whatever happens at n for x of n happens at, where does this happen? At n plus n naught, right? For phi of n. So we can say phi of n plus n naught is equal to x of n, right? If you substitute 0, you can see phi of n naught is equal to x of 0. So it matches. So now the opposite also is true, right? Whatever happens at n for x of phi of n happens at n minus n naught for x of n, right? So it is just replacing n with n minus n naught. So what I'll get? Phi of n is equal to x of n minus n naught. So this is my new signal, right? And I have shifted x of n by to right by n naught. So mathematically it is given as this structure. So phi of n is equal to x of n minus n naught. So this is nothing but right shift. What about left shift by n naught units? It will just be plus n naught. So shifting to the right by n naught units, my new signal phi of n will be x of n minus n naught. And shifting to the left by n naught units, my phi of n will be x of n plus n naught. Okay. So next we look at time scaling. So in scaling, what happens? The signal will either expand or contract, right? So again, we'll take x of n. So let's say this is something like this. Let's say 4, 5, 6. Again, this is, let's say 3, 1 and 0. So 0, 1, 2, 3, minus 1, minus 2, minus 3 and so on. Okay, so this is my x of n. Suppose I want to scale this by 2 times. So x of 2n. How will this look? Let me call it as phi 1 of n. Okay, so my n is here. 0, 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, minus 4, minus 5, okay? And this is my phi 1 of n. So my phi 1 of 0 is nothing but x of 2 into 0, which is nothing but x of 0 itself. My phi 1 of minus 1 is x of 2 into minus 1, which is x of minus 2. My phi 1 of 1 is x of 2. My phi 1 of minus 2 is x of minus 4. Phi 1 of 2 is x of 4, and so on, right? So you can observe that only the origin value is equal. All other values are nothing but the value at 2n for x, right? So at origin we can put the same value, which is 6. And at minus 1 it is x of minus 2, which is 4. And at plus 1 it is x of 2, which is 1. And at minus 2 and above that it is x of minus 4 and minus 6 and so on, but it is 0 outside that interval, so it is going to be 0 here. And again on the positive direction also it is going to be 0. So this is how you can generalize to scale the signal for x of a greater than 0. And what is happening? It is shrinking or contracting, right? So initially the extent was to from minus 2 to plus 2. Here it has gone from minus 1 to 1. So we call it as a time compression. So next we'll see time expansion. But you should also notice another problem here. Okay, we'll see it. So again, I'll take the same x of n. Let me put it here. So now I want to build a signal which is phi of n, or let's say phi dash of n, is equal to x of n by 2. So now you can see n is an integer, but n by 2 may not be an integer. It's integer only for even values. So what do I do then, right? So let's see whatever we can find out. So 0, 1, 2, 3, 4, 5, 6, minus 1, minus 2, minus 3, minus 4, minus 5 and so on, right? So my phi dash of 0 is nothing but again x of 0. My phi dash of 1 is x of 1, 1 by 2, right? Which I don't know. My phi dash of 2 is x of 1 and so on. And my phi dash of minus 1 is x of minus 1 by 2. My phi dash of minus 2 is x of minus 1 and so on. So these values I know, right? So I'll just put those down first. So I have 6 and phi dash of 2 is x of 1, which is 3. And my phi dash of 4 will be x of 2, which is 1, right? And on the negative side, my minus 2 will be 5 and minus 4 will be 4, correct? So here what I do is, I can just assume it as 0. So these terms I can assume it as 0. For simplicity, right? Because we don't have any value at that point. Or in some cases, we can also interpolate the signal. For example, if you use a linear interpolation, so you can see you can just connect these by a straight line. So you can see it is like this, right? 6 and then like this. So what will be its value here? Some 4.5, 5.5 and so on. You can find the value at these points as well. So it is like linear interpolation. Then you can put 5.5, 4.5 here, right? Otherwise, if you have the continuous signal, right? If you have the continuous signal and you have sampled that at these points and you got 4, 5, 6, and then you can get from, if you have the continuous time signal, you can get the values from here also, right? So if we don't have both these information and we don't want to do the linear interpolation, then we'll just assume this as 0. Okay, so it is a easier approach. So this also depends on what we require, right? So if you are actually going to convert this back into a continuous time signal, adding zeros may not make sense. We need to actually use some interpolation, or if we know the continuous time signals waveform, we have to use that. Okay. And again, as you have seen here, whatever is at 2 here, it has shifted to 4. So this is like a time expansion. And in general, your x of an for a less than 0. Okay. Again, this is less than 1 and this is greater than 1. I'm sorry for that. Less than 0, it will be negative and it will involve time reversal, right? Okay. So next we'll see that one. Time reversal. So this one is easy. You just have x of minus n, right? Replace x of 1 to x of minus n. So let me take my x of n as some signal. 5, 4, 4.5 and let's say 0, 1, 2. Here all zeros, okay? Minus 2, zeros. So what will be my x of minus n? It is just mirror about the y-axis. And whatever is in the origin, it will remain same. So my x of 5 will remain same. 4.5 will come here. And my 4 will come here. So 0, 1, 2, minus 1. These will be zeros. Yeah, this is my time reversal. So it is like a reflection about the vertical axis, right? And the origin is unchanged. So here also the origin is unchanged. So if it is a pure time scaling or time reversal, your origin is gonna be unchanged. Okay. So now let us look at the combined operations. Combined operations of shifting, scaling and reversal. So again, as you know, we have two methods. So in method 1, again I'll write the objective. Objective is to find phi of n such that it is equal to x of an plus b. So your a and b can be negative. Okay, it can belong to real numbers. But again, if you have a real number, there will be a problem, right? Again, with respect to time shifting, if b is a real number, it may not coincide with the integer values we are taking, n equal to 1, 2, 3. So then again, you have to assume it as 0, right? So for that constraint, we'll just call a can be negative and b is real. Sorry, b is integer. Okay. So method 1, what we are going to do is, we will have x of n. So first we do the time shifting. Time shift by b. So this is nothing but, in mathematical terms, replacing n with n minus b, right? We can take it as a right shift. So before this, I will also summarize for each thing what is happening. So your time shifting to the right, let's say, is replacing n with n minus b, and your time scaling is replacing n with an, and your time reversal is replacing n with minus l. And here a, you can just call it as some mod an so that it is positive. Okay, so we are decoupling the time scaling and time reversal. So again, coming to method 1, we are first shifting and then scaling. So what I will get? I will get x of n minus b. Okay, and then what should I do to get x of an minus b? I should do a time scaling by a. So time scaling by a. So again, I will do it with mod a. So mod a can be less than 1 or mod a greater than 1, right? So this mod a I'm doing because I'm decoupling time scaling and time reversal. If you want, you can do them both together. So I'll get x of mod a n minus b. Depending on whether mod a is less than 1 or greater than 1, I have to scale it appropriately. It will be a time compression or time expansion, right? So then I do the time reversal. Time reversal only if a is negative. A is negative. So then I will get my original signal, right? Whatever I require, x of an minus b. So if a is positive, then it will be directly an minus b. And if a is negative, I'll have another negative sign, making this again x of an minus b. Okay, so this together will nothing but time scaling by a. So this is my first method. So now let us look at method 2. So in this we are going to do the scaling first and then we'll do the shifting. So I have x of n, I time scale by mod a units, which is nothing but, which can be mod a less than 1 or mod a greater than 1. So I'll obtain x of mod a n, and then I time reversal if a is negative. So then I'll get x of an. So now what should I do to get x of an minus b? I should time shift by b by a. Time shift by b by a. So then I'll get x of a into n minus b by a. Because in time shifting, we have to replace n with n minus whatever the value is, right? So this is nothing but x of an minus b, which is what we wanted. So let us take an example. So I have x of n given by five. So 0, 1, 2, 3, minus 1, minus 2, minus 3. So it is 0 beyond this. And let's say 1, 2, 1, 3, 1. Okay. So then I want to find phi of, let's say, n by 2 plus 1. Okay. So what is my a here? A is 1 by 2 and b is minus 1 because we have taken it in the form of an minus b, right? Okay. So by our method 1, so first thing is time shift by minus 1. So my x of n plus 1 will be, I have to shift this to the left by 1. So I'll start with minus 3, minus 2, minus 1, 0, 1, 2, 3. So I have 1, 2, again 1, then 3, and then again 1, and then 0. So my second step is, I have to time scale by half. Time scale by half. So what will happen if I time scale it by half? It will just expand, right? So whatever is at minus 3 will go to minus 6. So I'll start from minus 6, minus 5, minus 1, minus 2, minus 3, minus 4. Same 1, 2, 3, 4. Okay, 0. So x of n by 2 plus 1. So my origin will remain same at 3. And then whatever is at 1 will go to 2. So this will be 1. And minus 2 is 1. Minus 4 is 2. And again minus 6 is 1. So in between we can just put zeros. So this is nothing but my this is phi of n equal to x of n by 2 plus 1. So this is my phi of n. So you can, to verify, you can just substitute and see. Let's say phi of 0, it should be equal to x of 1. So x of 1 is nothing but 3. Is it equal to phi of 0? Yes, it is equal. And some other thing also you can put. N equal to 2. 2 by 2 is 1. In phi of 2 is equal to x of 2. So phi of 2, x of 2 is 1. And phi of 2 is also 1. So we can verify by this way also. So my time reversal is not required. Not required. So otherwise, if it is minus n by 2, you have to just reflect it about the y-axis. So then in my method 2, what do I have? So I first time scale by half. So I just take x of n. So if I time scale 0, 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, minus 4, minus 5. So origin it is 1. And then at 1 I have 3, that will go to 2. At 2 I have 1, which will go here. So this is 1. And then at minus 1 I have 2, that will go to minus 2. And then at minus 2 I have 1, which will go to minus 4. Okay. This is my x of n by 2. So there is no time reversal here. So then we can jump straight to time scaling. Time shifting by b by a. So what is my b by a here? B is 1 and my a is, b is minus 1 and my a is half. So minus 1 by half, which is nothing but minus 2. So I have to time shift by minus 2. So my x of n by 2 plus 1. How is this obtained? 1 by 2 into n plus 2. This is nothing but my phi of n. So I start from minus 6, minus 5, minus 4, minus 3, minus 2, minus 1. 0, 1, 2, 3, 4 n. So I have to shift this signal to the left by 2 units, right? Okay, so my -4, it will go to -6, 1, 2, 1, 3 and 1 again. So you can see both these results are giving the same answer, and it should give the same answer only. Okay. And here again you can cross verify finally by substituting and seeing. The same we used for this. So now let us look at the classification of signals. So the first one we'll see is between periodic and aperiodic signals. Periodic and aperiodic. So what is a periodic signal? It repeats itself after a certain interval of time continuously. So if x of n, let's say x of n plus some n is equal to x of n for all n, and some n belongs to integer, then we say, or let's say positive integers, right, or natural numbers, then x of n is periodic. It can actually be any n, so we are not constraining, but for defining the time period or the signal period, we call it the smallest positive n. Okay, such that this is true, and it is also called as the fundamental signal period. Okay, so for periodic signal, you can already know that your energy is going to be infinite, and your power, it is just sufficient to calculate it over one period. So let's say it is periodic with n, then I'll just say 1 by n summation n equal to 0 to n x of n mod square. So it is also similar to saying if we know the information in one period, we also know the entire signal if it is periodic. Okay. So what about aperiodic signals? It is nothing but signals which are not periodic. Signals that are not periodic. So then we have causal signals. So causal signals are nothing but x of n should be equal to 0 for n less than 0. So such signals are called as causal signals. And if x of n not equal to 0 for n less than 0, any n, right? Even for one value of n it is not equal to 0, then we call it as non-causal. And if x of n is equal to 0 for n greater than 0, then we call it as anti-causal signals. Okay. And then we have something called as energy signal. So what is energy signal? signals having finite energy. Okay, so your Ex should be less than infinity. Such signals are called as energy signals. So then we also have power signals. So power signals are nothing but signals having finite and non-zero power. So signals having finite and non-zero power. So your Ex is anyway going to be equal to infinite because it has a finite and non-zero power. And your Px should be less than infinity. And also greater than 0. And it is also possible that certain signals are neither power nor energy signals. Are neither power or energy signals. Again, another aspect about periodic signals is it is a power signal, right? And also if you see, for a constant signal, right? Let's say it is a constant signal having amplitude of 2. So in continuous time case, we said the fundamental period is not defined. But in discrete time case, the fundamental period is one. Okay? Because the same signal is repeating after every one interval, correct? So the fundamental period here is 1. So here we do not have any ambiguity in defining the fundamental period. And your fundamental signal period should be a small positive n greater than 0. Right? It can't be equal to 0. So that clarifies this periodic signal, the fundamental period for a constant signal. Okay? So next we'll see even or odd signals. So even signal is defined like this. Your x of n is equal to x of minus n. Okay, so it is symmetric about the vertical axis. So it can be like this. X of 0 can be anything, but both sides it should be symmetric. Okay. And your odd signal, your x of n should be equal to minus x of minus n. So it is anti-symmetric about the vertical axis. So if the right side is this, your left side should be something like this. And this is for all n. Yeah. Okay. So there is one mistake in this. What is it? Let's say if your x of 0 is equal to minus x of 0, then 2x of 0 is equal to 0, which implies that your x of 0 itself is 0. So your x of 0 should always be 0. Right? For an odd signal. Okay? So this was also the case in your continuous time signals. So then you have few properties like your odd signal into odd will give you even, right? Because there will be two minus signs when you replace n with minus n. And even into even is also going to be even. And odd into even will be odd because there is only one negative sign. Similarly, your even into odd will also be odd. So this is just like multiplication of two signals. One of them can be either odd or even, and the other is also either odd or even. The four possibilities. And in general, any signal can be decomposed into its odd and even counterparts. So let's say you have a signal x of n, then you can define the even counterpart as x of n plus x of minus n by 2, and your odd counterpart as x of n minus x of minus n by 2. So, and you can write x of n as x even of n plus x odd of n. So this we did similar to the continuous time case only. Okay. So then we have the conjugate symmetric. So this is for complex signals. So conjugate symmetric, what we have is your x of n should be equal to x conjugate of n. Sorry, x conjugate of minus n. X of n equal to x conjugate of n is nothing but real signals, right? So for conjugate symmetric, your x of n should be equal to x conjugate of minus n. So if your x of n is given by some a of n plus j b of n, so then a of n plus j b of n is equal to a of n, a of minus n minus jb of n. Sorry, jb of minus n. So comparing, you will get a of n equal to a of minus n and b of n is equal to minus b of minus n. So a of n and b of n are real signals. So it means it is even in real part and odd in imaginary part. Okay, this is conjugate symmetric. And conjugate antisymmetric, so it is the same except for a minus sign. So we can just copy this. So your x of n will be equal to minus x star of minus n, and this will be have a plus sign here, minus sign here. So this will have a minus sign and this will have a plus sign. So in real part it is odd. So it is odd in real part and it is even in your imaginary part. So as our final topic for today, we have to study the useful signals. So some useful signals. So the first signal we'll be seeing is our unit impulse signal. So in discrete time case, there is no much complexity as we saw it in case of continuous time signals. Here we just define it as 0 for n not equal to 0, 1 for n equal to 0. Okay, it is not going to infinity, right? And it is represented by delta of n. So your delta of n is nothing but 1 here and 0 everywhere else. Again, similar to the discrete time case, we had the integral area equal to 1. Here we just have the summation n equal to minus infinity to infinity, delta of n is equal to nothing but delta of 0, which is equal to 1. And what are the two properties we saw? The multiplicative property, multiplication property. So if you have any signal x of n, you multiply it with delta of n, it will take the value x of 0 and we'll get delta of n. Only your whatever the value at x of 0 will exist, and everywhere else it will be equal to 0. And the second property is nothing but the shifting property, right? So here how it is, it's just summation n equal to minus infinity to infinity, x of n, delta of n. It will give us summation n equal to minus infinity to infinity, x of 0, delta of n. So x of 0 is a constant, it is just one single value. You can take it outside the integral, and then it's a summation of delta of n, which is equal to 1. So this is equal to x of 0. So we can just obtain a single value from the entire signal. So if you want to get x of n naught, what you have to do? So I have to write summation n equal to minus infinity to infinity, x of n, delta of n minus n naught, right? This will give the value of x of n naught. Okay. So this is all with the unit impulse signal. So next we'll see about the unit step. Again, how we define this? It is defined as u of n, and it is equal to 1 for n greater than or equal to 0, and 0 for n less than 0. So how will it look graphically? Zero, 1, 3, minus 1, minus 2, minus 3. So from 0 it will be 1. So less than 0, it is 0. Again, we can easily find the relation between the unit impulse and unit step signal. So first, your unit impulse is nothing but u of n, and then you take the shifted by 1 unit, u of n minus 1, and subtract them both. So you will just get a single value at 0, which is equal to 1, which is nothing but the unit impulse function. And our unit impulse function is nothing but just integral here is nothing but summation, right? So you sum, let's say m equal to minus infinity to n, and you have delta of m. So for n less than 0, it will just add up the sums until less than 0, so it will be 0. Well, as soon as n becomes 0, you will start to include this value, and it will continue to be 1 for n greater than or equal to 0. So next we will see about our complex exponential and sinusoidal signals. So these are very useful in Fourier series, right? So we have to take a look at this. And here it is slightly, one of the property is slightly different from the continuous time signal, which I'll let you know in a while. So your complex exponential and sinusoidal signal is given by x of n is equal to c alpha power n. So your c and alpha are complex numbers. So in the continuous time case, we had some e power alpha t, right? So here we are writing alpha itself as a base, right? This is just for convenience, because here in continuous time you have an integral. So when you have an integral, it is easier to represent in terms of e. But here you have summation. So in summation, if you have alpha or something, you can just write it as the sum, right? Something like this. So just for convenience, nothing else. So if you want, we can also represent it as some c e power beta n, such that alpha is equal to e power beta. This is always possible to write. Okay. So you can have a real exponentials. So in that case, your c and alpha are real. So then what do you expect? If alpha is greater than 1, you will expect a growing signal, exponentially growing signal, right? And if your alpha is less than 1, you will realize a exponentially decaying signal. Right? At infinity tends to 0. So this is some c alpha power n. And this is also some c alpha power n for different alphas. Okay. So what happens if alpha is negative? So at all the even integer values, you will get a positive value, right? So because alpha power 2n is positive and alpha power 2n plus 1 is negative. So at origin, you will have some positive value, here negative. So you will have this kind of behavior. And the exponential nature also carries over. So you have this exponentially decaying. Alright? So this is observed. So next, if you have just the sinusoidal signals. So your x of n is equal to a cos omega naught n plus some phi. Okay. So how will you write this? So you will have a sinusoidal nature, right? And at integer values, you will actually have the samples. So your signal will look like this. This is 0. Okay, so this red color will be your actual discrete time signal. And your units of omega naught and phi both will be in radians. Because n is just an integer, we are considering it has no units. So now the question arises, is x of n equal to a cos omega naught n plus phi always periodic? Right? So now let us check that. So I will take x of n plus n, which is nothing but cos omega naught n plus omega naught n plus phi. So for this to be equal to x of n, my omega naught n should be an integer multiple of 2 pi a, correct? So my omega naught itself should be a rational multiple of 2 pi. So my omega naught should be a rational multiple of 2 pi for x of n to be periodic. So if omega naught is just some 1, it is not a rational multiple of 2 pi. So x of n will not be periodic. Okay. So another example, if it is 2 pi by 3. So you can see there is a 2 pi factor. So x of n is periodic. So this constraint is important. This is one of the stark difference between continuous time signals and discrete time signals in terms of the complex exponentials or the sinusoidal signals here. And this arises as a matter of fact that your n is discretized and it can take only integer values. So let us take a look at the general complex exponential signals now, having both the real part and imaginary part. So my x of n was given by c alpha power n, right? I can in polar form write c as c e power j theta, right? Mod c e power j theta. And alpha I can write as mod alpha e power j omega naught. So my x of n will become mod c mod alpha e power j omega naught n plus theta. So this I can also write it as mod c mod alpha into cos of omega naught n plus theta plus j sine of omega naught n plus theta. So I will show you one example of how this can be plotted, like graphically. So let's say my mod alpha is greater than 1, okay? And here we missed the factor n, okay? So mod alpha is greater than 1 meaning it is just growing, right? And your real part is having some cosine of some omega naught n plus theta variation. So let's plot it. So first thing is we need to observe that it is growing exponentially. And then we have the sinusoidal variation. Okay. So combining these both, we can just try to so it will just continue to grow very rapidly, right? It will have a sinusoidal variation and will be bounded by this exponential curve. Okay. Okay guys, so that's it for today. See you in the next video. Until then, take care. Bye.